guys able to install the programs and run it? How many of you tried? Nobody tried. Okay. Please try and then let us know if there are any problems, because if there is a problem, then we need to fix it quickly. Okay. Okay, what did we cover last class? We were still doing unconstrained optimization. What did we talk about? We talked about different univariate minimization procedures. We talked about something like this. We said we always move in the opposite direction of the gradient, right? But choice of alpha k was the problem. What can go wrong with alpha? Yes, if it's close to 0, then what is the problem? Will fail, is it? If this is very close to 0, if it's very small? I mean, if alpha is very small, close to 0, you're guaranteed to reach the local minimum, but it'll be very slow. What if it's very large? Let's say it's very small. Very large. It can diverge. It does not. It might not converge. Okay. And what determines whether alpha is small or large? Yeah. K determines whether alpha is large or small. Roughly, what should alpha be in relation to the second derivative? 1 by rest. Yes, the alpha should be proportional to. So this is alpha. This is proportional. And in fact, we said the actual condition is if alpha should be less than 2 times w dash. Okay. And then we talked about Newton's method, which we already talked about in previous class. What is the Newton's method? Yeah, k plus 1, 6k. Okay. How is this an improvement over this? Over this method? Is it an improvement over this? Sorry? But so my question is this necessarily better than this? Is it always better than this? Right, of course here, f double dash of xk has to be greater than 0. When it is greater than 0, is it better than this? Well, in a way it is, right? Because we said the appropriate alpha to choose to prevent divergence should be proportional to 1 by f double dash. That's what we've done here. Alpha k is essentially 1 by f double dash. So yeah, this is an improvement whenever you have greater than 0. But when does it fail? Yes, so when f double dash of xk is less than 0, there is a problem. And what is the problem? Well, the sign is flipped. That means you're now moving away from the minimum. See, double dash xk tending to 0 is not always a problem, provided f dash of x is also tending to 0. Okay? Or in a way, if f double dash of xk is getting closer and closer to 0 faster than f dash, then you have a big number divided by a small number, then you can run into problems. But if both of them are kind of approaching 0 at kind of the same rate, then this ratio more or less remains constant. So that f double dash of xk getting smaller is not always a problem. If it is becoming small almost at the same rate as f dash, then you're not in trouble. If it's decaying towards zero faster than f dash, then you're in trouble because the denominator is becoming smaller faster than the numerator. That means this term is huge. Then also you're likely to run into trouble. Okay, and how do we fix this problem? It's the Levenberg method, where we say, well, we simply say we never allow the denominator to become negative. Right? Lambda is chosen such that this term is always positive. So this will address this issue. That means you will never now move away from, or you'll never move in the opposite direction of minus f dash of xk. But what is the downfall? Yeah. What is the problem? Okay, if lambda is very okay, let's assume we choose lambda large enough so that this never becomes negative. You guys have to revise. Yeah? Okay. Well, because you've added a positive number here, it means now if f double dash is positive, the denominator is a larger number than if lambda was not there. That means your alpha is smaller now. So you do lose some speed at which you converge towards the minimum, but at the expense of, or what you gain is you never let uh, this term become negative. All right. And then did we talk about multivariate? What did we talk about here? Well, here we said there are two things. We only had to choose alpha k. We always knew which direction to move. All we had to decide was alpha k. Okay. But here we have to decide both. Okay. And then we talked about line search. Once you've chosen direction in which to move, then we said the process of minimizing the function is essentially a univariate problem. Okay, of minimizing this function, okay, which is nothing but xk plus k. And then we talked about tracking to get alpha. What about decay? How do we choose decay? I mean, there are infinitely many directions in which you can move at any point xk when we are talking about unconstrained optimization. How do we choose decay then? Well, you choose decay such, or in fact, you choose both of these in such a way that your update equation is now like this. I can't remember what this was. Yeah, it was this alpha k. Okay, you choose this such that f of k plus 1 is what? Yes, you always ensure you choose them such that in the next step or when you move forward, the value of your function is lower. And if you keep doing this, hopefully you'll uh, reach a minimum. Convention is we always choose greater than 0. And the choice of decay that we saw so far was always negative of xk. That is because this is the direction along with what? Along which completed for me. This is the direction along which why do we choose negative of the gradient as the direction to move along? See, that's the negative sign. But why the gradient of f? What is special about the gradient of f? Well, there are several slopes now in higher dimensions. In if you yeah, sorry, repeat that again. No, this okay. The gradient does not always point in the direction in which the minimum exists. Gradient is a local property. It has no idea about what happens maybe 4 points away from this point. Right? So there is no way the gradient knows where the minimum of the function is. But what is special about the gradient? Yes. So the gradient alone is the direction in which the function increases the most. If I'm standing, let's say I'm standing on a two-dimensional, let's say we're searching over R2, I'm at this point. I mean, I can choose any direction out of the 360 degrees. The gradient points in the direction, and if I take a small step in that direction, the function increases the most along the gradient. But if I move in the exact opposite direction, then the function will decrease the most. So this is the direction along which the function decreases the most at xk, not any other point, where I am right now. Okay, I have a simulation, again, animation to demonstrate this. Let's see. To show that the gradient is in fact the direction along which the function reduces the most. Okay. All right. So this is some function f of x. This is my current point. The black line or a black arrow indicates the direction of the gradient. So it's pointing outwards. That means that's the direction in which the function increases the most. It's a bowl. And if you have a bowl, if you're at any point here, then the direction in which it increases the most is always pointing away from the bottom of the bowl. Okay. This red line, so hold on. So this is the line along the gradient. Okay. I earlier said the gradient does not point towards the minimum. In this case, in this particular function, the negative of the gradient does point towards the minimum. In this case of a this symmetric function. Okay. Now, if I move along this line, right, then it is equal, and I plot the value of the function as I move along that line. That's this black curve. Okay. And this red line is any direction, dk. It's some arbitrary direction that I choose. Okay. And now if I move along this line, the corresponding plot of this function f of x along that line is given by this red curve, and the intersection of these 2 points, which corresponds to t equals 0, is essentially this point. So all the points on this side correspond to negative values of t. All the points on this side on this line correspond to positive values of t, and similarly here. These are negative values of t and these are positive values of t. Now, the blue line here is the slope of this red curve. So if I move along this direction and I ask what is the slope of my function as I move along this, that's given by the blue line. Now, if I change this direction, I can change this direction. Okay, now if both of them match, right? Let's do that first. Then the red and black curve will match perfectly. So if I match them, okay. So if both of them if D points in the direction of plus gradient of f, this is how my function varies if I move along that line. And this is the slope. Okay. Now if I choose any other direction, right, just look at what happens to the slope. Okay. And please note that the slope is positive. That means the gradient tells me the direction in which my function increases always, okay, because the slope is positive. And if I move along that arrow, my function will increase. So if I move in the opposite direction, it should decrease. Now just look at the red curve and look at the slope. After a particular point, it's become negative. So here the slope is more or less 0. After this, it's negative. So if I choose any direction from now on, my function is likely to reduce because this blue line has a negative slope. Okay? And look at what point this negative slope is maximum, or it has the slope has the lowest value, lowest in the sense negative value. So here, if I look at directions in and around minus the gradient, the blue line will reach a lowest value and then it'll go back up again. Right? That means that is the lowest possible slope you can get, which is exactly when you move in the opposite direction of there. This is the maximum possible decrease you can get if you choose any direction to take a step in. And this is true everywhere. So no matter where you go, if you look at the blue line, it'll reach its largest negative slope only when it's pointing along uh, the negative gradient and not anywhere else. This is true for all other functions. Yes. But here, this is the problem with the Rosenbrock function. The slope is at some, as you get close to the valley, the slope is extremely small. That's why you don't see it that well. Okay, I hope that at least uh, gives you a visual proof, if not an actual formal proof, that this is actually, if I'm at a point xk, this is probably the best direction to take because this is the direction along which the function reduces the most. And if I take a small step in that direction by appropriately choosing alpha, then I am likely to satisfy this condition. Okay. Right. And then, but well, just because you chose the negative of the gradient as a direction to move, it does not mean you can choose any alpha. If you choose a large value for alpha, you can still get into trouble. And for that, we said we can use backtracking, where you always ensure that you choose an alpha such that this condition is satisfied, then you're safe. Then you never really diverge. Okay. See, and we said we always don't have to do an exact search. What is an exact search if you're doing a line search? Do you remember? Well, the exact search is you choose an alpha k such that this function is minimized. That means there is no other alpha that gives me a lower value for my function. So we are essentially then saying an exact search would be you choose alpha k is greater than 0 and an optimal value for alpha k, because if you choose any other value, you would not get the same amount of decrease in your function f of x k plus alpha k dk. But often we said we don't necessarily have to do the exact search. As long as you choose an alpha that simply lets you reduce this function in the current step, then you're fine. And if you simply keep doing that, then you're eventually like then you will reach the local minimum. Okay, and we saw some demonstrations last time, right? What what does happen if you do an exact search? It turns out if you do an exact search, something interesting happens. Um, if you so you're let's say you're at this point, right? And this is the direction you've chosen to move. This is your, let's say, this is your x. If you say you're choosing an exact search, then you're choosing an alpha such that so you decide to move in this direction. That's your negative. So that means if this is your x of k, you'll choose an alpha such that x of k plus 1 is this point. Okay? Because you're exactly solving for this. You're choosing an alpha such that you reach that point. Okay, that means at every step you are exactly solving this problem. That is, at every step after you've chosen a direction, you are reaching the point, the lowest point possible. It turns out when you do that, right? That means you jump from here to this point. This is your xk plus 1. And if you had moved any further, the function would increase again. This is the lowest possible value for the function that you could have obtained by moving along this line. Okay? And then now you have to decide a new direction. And it turns out whenever you do an exact search, the new direction that you will choose will always be perpendicular this direction. That means once you've done an exact search and you jump from xk to xk plus 1, you reach a point xk plus 1 such that the gradient at that point k plus 1 is actually perpendicular to the gradient at the point f of xk. Okay? So this is the gradient. That means now you will decide to move in this direction, and then you'll move until you reach a point where you get the lowest possible value for the function along this line. And then at this point again, the gradient will be perpendicular to this. And you essentially now, if you do exact search, you're always taking a step and moving in an orthogonal direction at every point compared to your previous point. So when you do exact search, f of the gradient at f of xk is the inner product of that with f of xk plus 1 is always 0. Now we should do an exact search. Yeah. And when you do that, when you choose the direction to be the negative of your gradient, and you choose your alpha k to be through an exact search, then that is called the steepest descent. So somebody says steepest descent, this is what they're talking about. Okay, here I could be anywhere. Okay, and for this function, when I do the exact search, I immediately reach the minimum in one step. Okay, that is because of the nature of this function. But if I had a different function, okay, something like this, I would choose this. Okay, let's say I choose this point. I take the first step that reaches there. Okay, and then I take the next step. Okay, and you see at each point, the new direction that you take is always orthogonal. And you also see that I'm here, and then this is at this point, this was my line of search. Okay, you reach a point such that that line along which you were searching was actually tangent to a contour. Okay, that is equivalent to saying the new search direction is orthogonal to my current direction. Okay, so that's what is essentially happening whenever you're doing steepest descent, where at every step you're getting to the lowest point possible, and then you're moving. All right. Well, steepest descent is great, but the only issue is at every point you have to solve this. Okay, I don't know if you see the number here. Okay, uh, the number is, think of it as the iteration number. I am, even though I show it as one step jumping from one point to another, there are a lot of iterations going on to find out, to solve this problem at every step. So that's essentially what I've put there. So you can do steepest descent, but you are going to have to do a lot of iteration. Okay. So this is great, but provided you can solve this very quickly. If you cannot solve this very quickly, then it's essentially the same issue. You might as well have done inexact search and made similar amount of progress, or maybe even progressed a little faster. Right. So this is if you, I mean, of course, we can't always do steepest descent. If you can't do that, then you kind of do backtracking and you accept that you cannot do an exact search. You do an inexact search and keep continuing your iteration. And all this because alpha k depends on the curvature of your function at any given point in time, any given point in space or your current location. And the question is, okay, what if you had access to the curvature of the nature of the, or how much the function curves at any given point. Okay, but before that, I'll point out one other problem uh, with the gradient descent method. See, in the univariate case, we had the same thing. So we had skin is alpha k f dash of x. We have to choose one alpha, right? Depending on the curvature of the function, this could either converge or diverge. But in the multivariate case, we're doing exactly the same, more or less. Yeah, that's fine. The difference between these two is this is a vector equation. Okay, this is from Rn. That means I'm really talking about n different univariate problems, each one of which looks like this: xk. The ith equation, k plus 1 comma I, is essentially minus alpha k. What will be the ith term here from the gradient? What is the gradient? What is the first term? That's fine. So what will this be here? Right. It's exactly like this, right? You're saying you change it depending on the derivative of the function at this point. Here you're saying here I only care about derivative along the xi direction, and depending on that I change this. That means, see, if there are n equations like this, right? Here we had to worry about, when we talked about curvature, we only had to worry about curvature along one direction, the value along x. But here there are n directions, right? So it's possible that you choose some alpha, that alpha works very well for some directions, but for other directions it actually diverges. So that can be a problem. So having just one alpha k can be problematic. It can be problematic when f of x has different curvature along different directions. Okay, and in fact, it is it's not just uh, it turns out that it it of course it depends on f of um, uh, the nature of f of x. It also depends on the units that you're using for the different variables that you're measuring. Okay, for example, if you had a function like this, x1 square plus x2 square, this was your function, and then you do the same. I mean, you find the gradient, and then let's say you have to minimize this for some value. You find the gradient, and then you let's say you've chosen some alpha, and that actually gives you a fairly good performance. But let's say instead of measuring this in some units, let's say I was measuring this in millimeters. Instead of that, let's say I measure this parameter x1 in centimeters. Okay, it means then my function now would be different. In the sense that now, instead of measuring x1 and x2, I'm now measuring in v1 and v2. v2 and x2 are the same. I've not changed the units. But here, let's say I've switched from millimeter to centimeter. That means now my new function v will be 100 times v1 square plus v2 square. Okay, what looked like a circle before, now if you plot the contours for this along x1, x2, they will all be circles. What about this? Be the contours for these. Well, any contour is x1 plus x square equals c. That means this contour for this is c. What is this? This is an equation of a circle. What is the equation? What is this? Equation of an ellipse, right? So it turns out now, and what will the ellipse look like in this case? Like this or like this? Flat or vertical? Let be flat, right? So, well, you can verify it will look like this. Okay. Now this is a problem. Now the same alpha will not work. Okay, it won't work because what symmetric bowl before is now it's not necessarily asymmetric, but it's not isotropic. For example, no matter which direction you move here, the surface looks the same. Whereas here it's not the same. If you move along this direction, it looks very flat. If you look in the orthogonal direction, it looks very steep. Okay? That means this alpha, which worked very well before for solving this problem, will not work here. Well, might not work here. It'll work very well in terms of converging along the V2 direction because the curvature in the V2 direction has not changed. It's exactly the same as that because x2 is V2. But x1 is now 10 times V1. Okay, that means the bowls become steeper in this direction. The bowls can squished along this direction. That means the slopes are larger. Okay, uh, so it's very well possible that you need to oscillate a lot in this direction. Worst case, you might diverge along the x1 direction, even though you're converging along the x2 or v2 direction. Okay, so the point I'm trying to make is if you have a single alpha and you simply change scales of your variables, uh, now you have to think of come up with a new alpha to solve the problem because now the curvature of your surface has changed. Okay, it's no different from the discussion that we had last time. If you had a parabola like this versus a parabola like this, it's a simple change of variables, right? You have to now find a new alpha because the curvature has changed. Here, the curvature has changed, but the curvature has changed uh, it could have changed differently in different directions. For example, instead of doing a transformation like this, I could have done a transformation which led to ellipses like this. So the only way to address this problem of not having a single alpha is to account for the curvature. And how do you get the curvature of a function in one dimension? Or what gives me the curvature of a function for a univariate function? The double derivative, right? And what is the multivariate equivalent of the double derivative? Right, that's a it, right? So now, at any given point, wherever you are, okay, if you compute the Hessian matrix, that will tell you how the function essentially curves in different directions. Okay. Okay. And the generalization of the Newton's method is simply this. So you find your new xk plus 1 from your current point by simply taking your, okay, what is the Newton's method in the univariate case? It was f dash divided by f double dash. F double dash was in the denominator. You take that. What is f dash in this case? In the multivariate case, it's simply, that's your Newton's method. And all you've done here is you've exactly accounted for, uh, assuming this is the Hessian at that point, you've accounted for the exact curvature function. And if you remember, in the univariate case, we arrived at the Newton's method by saying if at any point you know the value of the function, the first derivative and the second derivative, then you can fit a parabola and then you minimize, or you fit a quadratic function and you minimize the quadratic function to get the new point, right? If you do exactly the same process, if you know the value of the function, if you know the gradient and the Hessian, you fit a quadratic function and you find the minimum and you set that as the new point for your search, and that's exactly what you will get. And if your f of x that you started with was in fact a quadratic function, you will reach the solution in one step. That means if you are dealing with problems like quadratic problems, where f of x is a quadratic function, and you change variables. So here f was a function of x, but here I switched to another variable where the relationship between f and x was this. X was, you can verify this later on. Or x and v were related through a linear transformation, through matrix. Okay? So if you are dealing with quadratic functions, and if you're changing variables through linear transformations, then there is no problem at all. If you use the Newton's method, in both these cases, so you started from here, you would reach the optimal point in one step. That's because you're exactly accounting for the curvature of the function. So it doesn't matter how you change this, as long as it remains quadratic, you solve it in one step. Okay, that's a great thing about the Newton's method. But what is the condition on the Hessian? What is the condition on your second derivative in the univariate case for the Newton's method to work? Yes, here the univariate case f double dash had to be greater than 0. What do you think is the corresponding condition here? This is a matrix. What is the size of this matrix? What is the size of the n cross n? Here, your x of hk, well, let's just say this, it has to be greater than 0. If it's not positive definite or positive semi-definite, then you run into trouble. Why did we run into trouble in the univariate case? Because we had something like this, xk plus 1, xk minus f dash by f double dash. Why did we run into trouble when f double dash was negative? Right, because this negative sign was flipped. Okay, it turns out that's exactly what happens here. Okay, because if, and that is why, I mean, that goes back to the idea of the positive definite matrix. What is the definition of a positive definite matrix? Okay, what does this mean geometrically? Have you thought about what this means geometrically? What I mean by that is this. Okay. What is the relationship? So if you can separate this into two terms, x vector, inner product with some y vector. What is when you say this is greater than or equal to 0, or in fact, if it's positive definite, it's definitely greater than 0. Okay. What does it mean to say the inner product of standard inner product between two vectors is greater than 0? Sorry? Okay, not similar, is it? What do you mean? Well, if A is I, x transpose x is a positive number. They're exactly the same vectors, right? Okay, here. You started with some x. What is, when you multiply a vector by a matrix A, what does it do? Or what all can it do? Scale, mirror, and rotate. Okay, all right. Okay. Let's say this is y. Okay. Y can be any vector now in R2, right? We're talking about R2. Y could be this, 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 this. But the condition here is x transpose y has to be positive. If you have that condition, does it mean now y can be any of these vectors? What are the possible y's you can get? Do they have to be exactly the same? No, greater than 0. If it's 0, then it's orthogonal. If A is skew symmetric a skew symmetric matrix will always rotate a vector x by 90 degrees. That's why x transpose a skew symmetric matrix multiplied by x will always be 0, because a skew symmetric matrix rotates the vector by 90 degrees. What this means is, here, if this is the orthogonal to x, right, ax has to be, okay, see, if this is a line, let's say this separates your R2 space into two spaces, this space and this space. When you have a positive definite matrix, it means whenever you have a positive definite matrix and you multiply a vector through that matrix will never rotate the vector x by more than plus or minus 90 degrees, right? That means my y can only be one of these vectors. It cannot even be an orthogonal vector, because this is always greater than 0. It will never flip the direction of x, okay? And geometrically now, the requirement that h of xk has to be greater than 0 or positive definite should make sense now again, because if this is positive definite, multiplying a positive inverse of a positive definite matrix is a positive definite matrix. Multiplying the gradient vector or negative of the gradient vector by a positive definite matrix will mean that you will never flip the direction in which you have to. The resulting direction that you get will always have a component along the gradient. That means you will definitely reduce the function. Okay? So that is where they are equivalent. Okay? F negative being changes the sign here. This being not positive definite means that you now flip the direction of the gradient given by the gradient function in a direction that is opposite to, not necessarily, or a component that is opposite to the direction of the negative of the gradient. Okay? So that's a geometric explanation for what positive definite means and why in this particular equation it has to be positive definite. Let's look at my demonstration again. Okay, this is the Newton's method. So this is a quadratic function. Okay, that means if I only need one step to get to the minimum. You do the Newton's method. This will, no matter where you start from, you always reach the minimum in one. Well, now you could say, well, the exact search did the same thing. So what is special? Okay, what is special is now if you go to this, the exact search never reached the minimum in one step. It always took these orthogonal directions to get there. But if you do the Newton's method, no matter where you start, you always reach the minimum at one step, because the quadratic function is a function with a fixed curvature, and the Hessian of a quadratic function is essentially gives you the curvature. That means you exactly account for how the surface is curved in different directions, so that in one step you get to the minimum. This also means if you have objective functions that are quadratic, you don't have to really do an iterative method. Well, that is an iterative method, but you always only need one iteration, provided you have access to the Hessian matrix. Now, let's go to the tricky one, this one. Right? This was always a problem. Okay? Do you remember what the problem was? Well, let's look at gradient descent first. Okay. You remember with the gradient descent, you can blow up if your alpha is too large. Now, if I make my alpha really small, sorry, this is a bit slow. Okay, I made it very small. Hopefully now it won't. Okay, all right. If I make alpha really small, it finds the valley, but after that the progress is extremely slow because it's very flat. Okay, this will go on forever. Okay, now you do the Newton's method. Okay, at every point, now you don't have to worry about choosing an alpha. You're asking, how does the surface curve? Where is the gradient? What is the direction of the gradient? How does the curvature of the surface look like? And you're essentially doing that step. Well, did it blow? No. There, it's done. It did some weird stuff, but it reaches there immediately. 4 steps, which you could not have done with your gradient descent, because your alpha had the appropriate alpha had to be different each time. In fact, even when you did the exact search will get you to the valley, but after that the search is still slow because the gradient in along one of the directions is really small. Okay, well, the Newton's method works great for this, right, which was problematic for all other methods. But everybody has a nemesis, and this function is the Newton's method's nemesis. This is the equivalent of this 1 minus e power x square function, where if you start very close, f double dash was positive, whereas at these points, f double dash is less than 0. That's exactly the case here. If you start somewhere very close, the Hessian matrix is positive definite, but everywhere outside, the Hessian matrix is not positive definite. There, you move away. I start from another point, move away, move away. Let's see, I move away. Let me see if I can get the point close there. If you start close enough, then you reach there, because there the Hessian is positive definite, and you reached fairly quickly because it's very well approximated by a quadratic function here when you start closing. Okay? But if you start outside, there is a problem. Okay? That's primarily because your h of x is in fact has got eigenvalues, some eigenvalues at least, that are negative. How do we address this problem? What did we do in the univariate case? Yeah, okay. How do we do that here? Okay, all right, good. Why lambda I? Okay, if I said if the problem here is at some points in your search space, this becomes non-definite. That means some eigenvalues might be positive, some might be negative. Okay, that means neither h of xk or minus h of xk are positive definite. You're saying let's add lambda I. Okay, lambda is a scalar, right? This is an n cross n matrix. This is n cross n. What is the purpose of this? And what is the value of lambda? Or is there any restriction on lambda? Okay, all right. It has to be greater than 0. Fine. But why will this help? Remember, the problem is some eigenvalues are negative. And you're saying this will fix it. You're right, it'll fix it. But why? Why does it fix it? We'll have to go back to eigenvalue D. What is the eigenvalue decomposition of this matrix? Or what is eigenvalue decomposition for a square matrix? Well, this is a symmetric matrix. What do we know about symmetric matrices and their eigenvalues? No. If they're positive, then it's positive definite. Well, if you have a symmetric matrix, so if you have a matrix A, the eigenvalue decomposition is given by this in general. Okay. What are these? What is this? This is a diagonal matrix with the eigenvalues as the diagonal entries. What is this? That's a matrix though. This is not a vector. You're right. Where are the eigenvectors in this matrix? Yes. The columns form the eigenvector. Fine. Okay. All right. If it's a symmetric matrix, what do we know? We know the eigenvalues will always be real. Sorry? No, this is always diagonal, no? Well, assuming this is diagonalizable, let's say we don't have to worry about the case where it cannot be diagonalized. In fact, symmetric matrices can always be diagonalized. Because Hessian is a symmetric matrix, so we always have an eigenvalue decomposition. The eigenvalues are all real, no complex values, and the eigenvectors can be chosen to be orthogonal to each other. That means your eigenvalue decomposition is really this. Okay, if the eigenvectors can be orthogonal to each other. That means you can write, and if you normalize the length, then this is an orthogonal matrix. The inverse of an orthogonal matrix is a transpose. So this we know, okay? In fact, what we know is this is indefinite. That means we have V, and then we have some positive entries. I'll just write some positive entries, and then some negative entries. These are the groups. And we have V transpose. Okay? You're saying this will address this problem. Why will it address the problem? Okay, well, let's write it down. So you're saying V lambda V transpose plus some lambda I. You're saying this is, if you choose an appropriate alpha, you're saying this is positive definite. Why? Well, okay. Again, a trick. I can be written like this. That means this is equivalent to a matrix whose eigenvalues are all lambda, with V and V having the eigenvectors as its columns. That means if you can combine these two. That means now if you take V out on this side and V transpose out on this side, then you have lambda plus. Whereas this one has some positive elements and some negative elements. As long as you choose lambda to be larger than the lowest negative element here, then the sum of these two will result in all positive diagonal entries. That means this whole matrix will be positive definite. Okay? That way, so all you have to change with the modification for the Levenberg Marquardt method, I'll simply write with LM, is this. Instead of using h of xk, you say xk plus 1 is xk minus what? Well, still want to move in the direction. Okay? So this will simply be h of xk plus lambda I. That's all. Okay? And in fact, if you implement this for this method, you will always come in. And I've written it as mu here. I chose lambda to be 1. But it's possible if I'd chosen a very small positive value, then it might still not converge because some of these eigenvalues might still be negative. So this might not be positive definite. But as long as I choose my lambda to be large enough, then you always move into. Okay? You're never now moving in the direction of the gradient. You're always moving at least to some extent along the negative of the gradient. All right. So that's all I wanted to say about unconstrained optimization. If there are, I mean, of course, there are lots of other methods. I've simply given you a flavor of some methods that are very basic. Okay. I hope this at least sets you off so that you can go self-study other methods when you need to. Are there any questions with unconstrained optimization before we proceed to the next topic? Okay. Now we'll move to the next topic. Well, on constrained stuff. That means now we're almost never looking for, I mean, most optimization methods come with some restriction because you're not interested in any possible parameter that value that could be obtained. There is a range that usually makes sense. Right? And our standard method was, what is this? Oh, there are P inequality constraints and Q equality constraints. X belongs to Rn. So now, see, in the earlier case, when we were searching for an x, let's say we're talking about R2, the entire space was available to us. We could search anywhere we want to find out the lowest possible value for the function that we could obtain. Okay, and that means when we say the entire space is available, that means no matter where I am free to search in any 360 degrees, right? I can decide to move in any direction I want. But the moment you move into a constrained situation, you are restricted. Okay, you cannot. It's possible that you are now restricted to, let's say, a region like this. Okay, the problem now is to find your f of x is the same. It behaves the same way as it did in the unconstrained case, except now you are not allowed to choose any value for x. You are only allowed to choose values that fall within this some set. Okay, let's call it omega. Okay, so when we are talking about constraint optimization, we are essentially talking about minimize f of x, but x now does not belong to Rn. X only belongs to this, and this is some subset of Rn. Okay, there is a small region over which we are interested in searching, and anything outside that is no go. We are absolutely not interested. So you really cannot violate this condition. Okay, if you find a value outside and say, oh, this value is quite low, f of x is quite low here, we don't care because this is not realistic for us. Okay, why it might not be realistic is maybe because your x is a bunch of lengths for some structure that you're building. If it returns you a negative value, that really does not make sense. So situations like that. Okay. See, then the question is, okay, how would we now find out uh, whether or not, well, whether or not if let's say I am at some point and all I know is the local property of the function at that point. Maybe the value of the function, maybe the gradient, and maybe the second derivative. Nothing else. Okay. How do I know whether or not this is actually minimum? That everything else out there is actually larger than me, and so I've actually reached the optimal value. Okay. And here, see, sometimes you might have this set with you, or this set would essentially be defined by your constraint. So here, sigma could be, or omega could be the set of all values in Rn such that g of x is less than or equal to 0, h of x equals 0. Okay. That's another way to think about what uh, what this is. This could have been obtained through your inequality and equality constraint. Okay. And whenever you have a problem like this, you are only always searching uh, the space along a set of feasible points. Right? And the point is feasible as long as it belongs to omega. So x is a feasible point if it belongs to me. If it does not belong, it's not a feasible point. That means, and the solution to this problem has to be a point from the feasible set of feasible points, omega. So it turns out to understand, to get an idea about whether or not uh, a, a point in omega is a local minimum. Right? What is the condition in the previous case, in the unconstrained case, for a point in Rn to be a local minimum? Unconstrained. What is the condition? No, yes, in Rn, the multivariate case. Okay, gradient is what? Okay. Well, if it's greater than 0, for sure it's a strict minimum, but this is also okay. You can also have 0 and it might still be a local minimum. Okay? This is the condition. It turns out when you have constrained problem, it's not this straightforward. There are some cases that we'll have to uh, deal with carefully. Okay? If so if you have this set, right, we'll distinguish two types of points. Okay, one is an interior point. I'm not going to formally define this, but you understand what I mean by an interior point. It's inside the set. On the other hand, you might have what are called boundary points. One way to think for this is if you're an interior point, you can always move in any possible direction, provided you might not be able to take a large step. You can always take an infinitesimally small step in any direction you want, okay, if you're inside. Okay? So even if I'm very close to the boundary but inside, that means I still have some room to move in this direction and still be in the set. Okay? Whereas for the boundary point, it turns out you cannot move in any arbitrary direction you want. For example, if I'm here, right, I can move in these directions, but I definitely cannot move in this direction. So there are directions that you cannot move if you're on the boundary. So that would be the difference between what is an interior point and what is a boundary point. So at any point in this set omega x, we say a direction D is feasible or is a feasible direction. Okay. Well, the formal definition is based on what I said. You can move, if you can move in any arbitrary direction by even a very, very small amount, uh, then it's an interior point. If it's here, then there are directions in which you cannot move. So at any point, all the directions that are allowed, uh, essentially directions along which if you move, you still stay in the set, those are called feasible directions. Right? So if for an interior point, all directions are feasible. For the boundary point, it's a restricted set. You cannot move in any arbitrary direction you want. Okay. I won't write down the formal definition, but it's in the slide, so you can check that out. Okay. Right. So now I'll simply write down the condition and then we'll try and understand this a little bit. Okay. The first order condition, right? If you're on a boundary point, it's slightly different depending on whether you're in the boundary or you're inside the set. If you're on the boundary point, right, as long as, let's say, you know the gradient of the function at that point, let's say the point that we're talking about is this x star function. Okay? The gradient of the function at x star, the inner product of that with any possible feasible direction. Okay, you're at this point. There are a set of feasible directions in which you can move. Okay, it's a boundary point. If this is greater than or equal to 0, this is the first order condition for a point to be a minimum. Okay. Okay. This might sound a little, look a little weird, but it's geometrically it's very simple. Okay. This essentially means, well, we just saw that earlier. What does it mean to say the inner product between two vectors is greater than or equal to 0? Or what can you say about the angle between the two vectors? So if I have a boundary point, let's say I'm at this point, the all possible uh, feasible directions are basically in or these directions along. I cannot move beyond these two lines. So I can move anywhere, all the possible directions at this. And the condition is the inner product of the gradient of the function. Remember, this is your omega. This is not your f of x. F of x is the surface. Okay. And these are the contours for your f of x. Okay. I'm probably losing some of you already. Let's recap. Okay. Let's say we are talking about, let's do R2, it's easier. R2. Okay. In the unconstrained case, let's say this is R2. My f of x was this surface that was coming out of the board. Right? That's clear. Okay. And then we said, well, we can't I cannot draw with chalk in 3D, but I'll simply draw the contours. Okay. Let's say these are my, I'll draw simpler contours. Let's say these are my contours. Is it clear? That's f of x, okay, in R2. Okay. Each of these lines corresponds to a constant value for my function f of x. Okay. Let's say this was -1, this was 0, 1, 2, 3. That means the surface is essentially increasing like this. Value is increasing. This is the contour. In the unconstrained case, you could search anywhere you want in R2 to find out the best possible solution. But if you're talking about a constrained optimization situation, you can't search anywhere you want. There is a region you're allowed to search, and that's it. Let's say this. This is my constraint set. Well, the contours describe how my function f of x is varying, but I can only move within this region. This is my constraint omega. Now the question is, what is the if I'm at a particular point, how do I figure out whether or not that point is actually a minimum using just the local properties? Okay, and the condition for that is, okay, if you're at a boundary point. So this is the first condition corresponds to all the points that are on the boundary. Okay, if I'm at the boundary, I have a set of feasible. Let's say I'm here. This is my x star. I have a set of feasible directions. That's basically all directions pointing away from this point here in this. I can move in. I cannot move in any other direction beyond this line. So I can move here. The condition is the inner product of the gradient of the function, okay, with that of all possible feasible directions has to be greater than 0. Okay. Geometrically, what does it mean to say the inner product between two vectors is greater than 0? No, hold on. Inner product is greater than 0 is orthogonal. Sorry, greater than 90, is it? Hey, if it's positive, yeah, it's less than, not 180. It's within plus or minus 90. So if I have a vector here, these are vectors. I mean, if I have a vector along this line, then that's at 90 degrees. It's a set of all vectors, all these vectors on this side of the line. They will all, so this is x, and if any one of these is y, then x transpose y will be greater than or equal to 0. Well, if I don't include anything on the line, then it will always be greater than 0. Okay. Now, this says the inner product of the gradient of the function and all possible directions has to be greater than 0. That means I'm at the boundary. These are all the points that I'm allowed to move. And if the gradient is has a component in any of my feasible directions, and the gradient points in the direction in which the function increases, that means anytime I move in a feasible direction, my function is going to go up. The value of my function is going to go up. That means the point I am at is actually a minimum, because any feasible direction I move, my function goes up. And that is my function. The statement that I made, any feasible direction I move, my function goes up, is this. That's what this means. Okay? Maybe I should have started it. I should have started with that. If you have a set of feasible directions, and if you move in any of your feasible directions, the value of the function goes up, then that point is a minimum. Okay, and that the math, you would state that mathematically like this. Okay, so if you have a point like that, then you're okay. Is this point, so given that I've drawn the contours like this, so that means the contour that goes through this point is this, assuming it's a continuous function. What direction is the gradient at this point? Where? Inside or outside? Hey, hold on. I just wrote down the value here. This is -1, 0, 1. This is probably 1.8. This is 2. This is 3. This line corresponds to f of x equals 3. This line corresponds to f of x equals 2. So which direction is my gradient pointing at this point? Outside, because it's the direction in which the function increases, right? So this is my gradient. This is my, okay. What are all the possible feasible directions here? Yeah. Well, It's all of these. What can you say about the inner product between the feasible directions and will it be positive? Well, it won't be, right? Here, if you choose any direction, what is the angle between them? It's greater than 90. That means the inner product will be negative. Okay, similarly, if you choose any one of these, it will be negative. Okay? What about this point? Let's say this is -2, this is -2.1. What are the feasible directions here? Right. Well, these have to be directions that lead me into the set. So that has to be, these are all the possible directions I can move. What is the direction of the gradient? The gradient is like this. And the orthogonal to the gradient is this line. All the points, all the feasible directions at this point are within that this line. That means no matter what feasible direction you choose, you are always increasing your function. That means this point has to be the minimum. Okay, I hope that clarifies the picture. The algebra is secondary. As long as you remember this picture, I think that's fine. And then you can connect the algebra to this. Yeah, so that's the idea, and that's essentially the first order condition for knowing whether or not, if it's greater than 0, for sure the issue is solved. This point is a minimum and you're done. Okay, there could be multiple points, but you're done. Okay, that's for a boundary. What about an interior point? Well, it turns out this is actually a general condition. This is actually the most general condition. If you want to find out if a point is a minimum, then the inner product of the gradient of a function with all possible feasible directions should be greater than or equal to 0. Okay. It turns out if it's an interior point, then this condition will simplify to because the only way this can be greater than or equal to 0 for all for example, if D can be any vector in Rn, this is some fixed vector, right? That means I can always choose, if this is a minimum point, x star is a minimum point, that means I can always choose my direction to be minus of gradient of f to get a negative value here. Okay, and if this is a minimum point and this condition has to be satisfied, the only way this condition will be satisfied for all possible D is this was. Right? So this is in fact a more general, as I said, more general condition. That means both the unconstrained optimization case and the constrained optimization case, this is the actual condition. Okay. Okay. And in fact, it also makes sense that this, for the interior point, it comes out to this, because the interior point is essentially like unconstrained optimization. So provided you don't move too far away. And for the unconstrained optimization case, this was the condition. Okay. All right. So here at the boundary, if you have f of x, suppose b greater than 0, then it's a minimum. Okay, that point x is a minimum. But you cannot know for sure if, sorry, if this is 0, because it can be greater than or equal to 0. If it in fact is equal to 0, then this is, I mean, you don't know. Okay? It could be anything. Okay? Then you have to look at the second order condition. If h of x is the Hessian, okay, at this point, then if D is any feasible point at x star, and if this is always greater than or equal to 0, that means h of x is positive definite with respect to all the feasible directions. Okay, then you have then this is a necessary condition. Well, that's what I've written. This is necessary, but if it's strictly greater than 0, then for sure this is sufficient. This point is a minimum. Okay, the equal to 0 condition can still happen. This the h of the Hessian matrix could be positive semi-definite with respect to your feasible directions, and it could actually be equal to 0, and it could still be a minimum point. That will require additional analysis. You can't just say from the second order condition. Okay. We'll continue for 10 more minutes. We'll do a couple of examples, and then maybe, hopefully, that will clarify things. In fact, we can apply the same rules for univariate case as well. You can talk about univariate constraint optimization. That means if you're not searching over all possible R, you're only searching over some finite interval. Let's do the univariate case first. Let's say, okay, the first one. F x equals x, and our problem is minimize x belonging to 0, 1 f of x. The plot looks like this, and we're only searching between 0 and 1. Next. The question is, use the condition, the first order or second order condition, find out where the minimum is. Well, at any point we need the gradient. What is the gradient? Well, in this case, it's just the first derivative. It's 1. What about second derivative? 0. Okay, it's flat. All right. Now, there are two boundary points. What are the two boundary points here? 0 and 1. Okay. Maybe let's first search the boundary points. If you're here, what are all the feasible directions at 0? What direction can you move? Well, you can only move to the right, right? That means I'll call it +1. That means I can only move in the positive direction. Okay, so that's my D. That's the only possible feasible direction. So now, what is the condition for the first order condition for checking if a point is a minimum? F dash. Well, inner product is simply scalar multiplication here because we are talking about stuff in 1D. This is, what is this? This is 1 multiplied by 1. This is in fact greater than 0. That means we are done. This is a minimum. Okay, because the inner product is greater than 0. Okay, what about, well, okay, so it looks like this is a local minimum. What about x equals 1? What is the feasible direction there? It's -1. What is f dash of D? Well, x is 1, f dash is still 1. So this is 1 multiplied by -1. This is less than 0. This is not. That is not a minimum because it does not satisfy the condition greater than or equal to 0. It's negative. That means the only feasible direction um, is this direction. And if I move in that direction, the value of my function goes down. That means I cannot be at a minimum because there are other points in my feasible set where the value of the function is lower. Whereas here, the only feasible direction is to the right. Okay. And if I move in that direction, the value of my function goes up. That means I'm at a minimum. I don't have to move anywhere. Okay. That's the minimum. Right. Okay. Let's do another example. What does this look like? What is the plot of this? We are only searching over 0 and 1. What is the plot of f of x? Okay, like this. No. Okay, we start from 1 and then it goes to 0 here, right? Like this. Is that okay? Okay. Hey, okay. Here, what about the interior points? Are there any minimum in the interior points? Before we didn't. We found that 0 is a local minimum, 1 is not. So we've sorted out the boundary. Are there any points inside? How? But you're saying no. Yes, it looks like there isn't. But how do you verify that? How will you show it using the first order condition? Yeah. Yes. What is it? F dash is 1, right? Choose any interior point x. Okay. X. Fine. What are the feasible directions here? Uh, F dash is 1. What are the feasible? So this is some internal point. Let's say 0.5. What are the feasible directions here? Here, what directions can I move? No, or minus 1, right? So all the possible feasible directions are minus 1 and plus 1. My f dash is 1. That means f dash of d. My condition is for any feasible direction, f dash of d has to be greater than or equal to 0. And that's not satisfied here. If I choose my direction to be 1, this is positive. But if I choose it as minus 1, it's not satisfied. That means no, in fact, any internal point does not have a local minimum inside because this is not satisfied. Okay. Yeah. What about this? Let's first do the boundary points. X equals 0, and then we'll also look at some internal interior points. Yeah. What is f dash d? D is plus 1. That's the only possibility. F dash of what? Oh, sorry. Okay. F dash is minus 1. Okay. What about f dash d? Well, at x equals 0, f dash is minus 2. This is equal to minus 2. So this is not. That that is not. So this is not. What about this one? What about x equals 1? What is the feasible direction? Minus 1. What is f dash at x equals 1? 2 times x minus 1. It's 2. No, it's 0. Okay. That means f dash of into d is 0. Well, we are not done. Well, it's not violated. It can be greater than or equal to 0. It's 0. Now, how do we verify? What is the next thing we do? If it's 0, then you have to look at the second order condition. What is the second derivative? Okay. F double dash is 2. Okay. That means, well, d transpose Hessian d has to be greater than or equal to 0. The scalar case, all of the scalars. That means f double dash d square has to be greater than or equal to 0. 2, d is minus 1, minus 1 square. So this is 2. So this is in fact, this is greater than 0. So this is in fact a strict minimum at this point. Okay. What about internal points? Are there any internal points that might be a local minimum? Well, I'll leave it to you guys for you to do. Let's do just one more and then we're done. this one. Again, um, sorry, x belongs to x. This is omega. What does this look like? Like this, is it? Are you sure? Is it like this? Like this? It's not. No, this is not the one. Well, it's minus x square. X square is like this, minus x square is like this. That means it's got to be a flip inverted parabola, and in fact, it's like this. Now let's do the same thing. Is there a minimum? X equals 0 will be a minimum, yes. So here, f dash of, in fact, it will be strictly greater than 0. What about this point? What is the first order condition there? Here, it's 0. It'll be 0 because the derivative goes to 0 here. But that means we don't know yet, right? So that means you'll have to use the second order condition. What is the second order condition? If yes, d square will be minus 2. That means this is not. All right, that's all. Okay. We'll stop here for today, and then we'll continue this tomorrow. We'll have a quiz tomorrow, and then we'll continue. Are there any questions? No? Okay, all right. Thank you.